Okay, tsunami hit, I guess almost an hour later, or a little later, and the first thing that happened is the diesel generators failed. They stopped. So now we didn't have any more power to those pumps that were cooling water in the core, but they had a backup system. They had batteries, 125 volt DC batteries. These are big batteries, and they had DC systems, steam-driven DC systems that could continue to cool the reactor. So this was one of their backup systems, and effectively what happens is the reactor's still hot, you're producing steam in the reactor even though the reactor's shut down, so you have steam in the top there. That steam is coming out, running a turbine, that turbine is turning a pump, that pump is pumping water back into the reactor, so you have a continuous cycle, and the reactor is still being maintained properly, not a problem. And again, this, as we understand it, worked fine. What happened, though, about 2 hours later, is the batteries were depleted. Okay, so now the controls for that turbine stopped. We still have decay heat in the reactor core. The reactor core is still very hot. So inside the reactor, you're still making steam. That reactor is starting to build up in pressure, just like your hot water heater might do at your house or your furnace might do at your house. And we have a relief valve that just relieves pressure to protect the reactor vessel. And that relief valve operated as designed. It opened up to relieve pressure from the reactor. And as I told you earlier, it relieves the pressure into the suppression pool, which is this huge, I call it a swimming pool, with cool water in it, and it quenches the steam. And that seemed to have worked fine, except now we can no longer we have steam coming out of the reactor, we don't have water going back into the reactor, so the inventory of water in the reactor is starting to become depleted. And as that happens, okay, the core starts to uncover. One of the worst things that can happen in a nuclear reactor is you uncover the core because it is very hot. It's in the neighborhood of 2,800 degrees Celsius. I don't know, I can't do the math that quickly, but 5,000 degrees or so. And we have no ability to cool the reactor. The other thing that happens is once those fuel rods get as hot as about 5,000 degrees, they start to react with the water differently, and they produce hydrogen gases given off, and that's where the hydrogen came from that we heard about. So now the core is uncovered, it's very hot, we're generating pressure and we're generating hydrogen in the reactor vessel. That hydrogen and pressure is being relieved through the pressure valve, through the pressure relief valve, down into the suppression chamber. It's still okay, we're not in a real dire situation yet. But what started to happen now is the pressure in the primary building, or in the torus and the primary containment, started to build up. And what the engineers decided to do was, rather than lose the primary containment, have the primary containment fail, they decided to vent the primary containment into the secondary containment and vent some of that pressure off, which actually is not a bad idea because you do want to make sure that you protect the primary containment. And they did that, and this is one of the unknowns right now. We're not quite sure how they did that. There were different vent paths that they could have used, and that's one of the things we're still trying to figure out. But what they ultimately did, we understand, is they vented that pressure from the primary containment into the secondary containment building. Now, the secondary containment building is a regular industrial building. It's not designed to withstand a whole lot of pressure, but they had a hydrogen accumulation now in the top of the building. There's also all types of electronic equipment, pumps, motors, valves in that system, or in that secondary building. And something sparked, which caused the ignition. Everybody saw it on TV. And that was the secondary containment building, not the primary containment building as we understand it. But we saw pictures of the secondary containment buildings exploding on reactors. And they did the same thing over and over again on units 1, 2, and 3. Okay, and we saw that over the series of a day or two as that went on. Okay, couple of points here. Let me just catch up on the slides. Saw the explosions. Okay, and where the units are today, as we understand them, we think there is core damage. In fact, we're sure there's core damage on Unit 1 and very probably 2 and 3. Core damage is those tubes with the uranium in them have probably melted. Okay, and on Unit 1, they've probably gotten so hot that they've probably melted toward the bottom of the reactor vessel, and actually there may be some pinhole leaks in the bottom of the reactor vessel. So that's pretty significant. We're not sure about the extent of the damage on Units 2 and 3 yet, but it's probably something along those lines. So what the Japanese did is they actually flooded that entire interior primary containment. So now they have a closed loop, the reactor cores are covered, and they're discharging and making up water, still attempting to keep the reactor fuel cool, and they seem to be making progress on that. But those 3 primary containments are flooded. Interestingly enough, if you recall, people were worried about the spent fuel in Unit 4 because all that fuel was out of the reactor and it was in the spent fuel pool. Up on the upper right of that picture, and I should have pointed it out earlier, is the spent fuel pool. The newspapers, the press, everybody was worried that because they couldn't make up water in the spent fuel pool, that fuel was also hot, thermally hot, and they thought it was boiling water off of the spent fuel pool and uncovering that fuel. And if you uncover that fuel, you have the same problem. You generate hydrogen, hydrogen forms in the building, and you get an explosion. And everybody was talking about the spent fuel being a problem. What we understand today, though, after they've taken some of those overhead pictures, that the spent fuel in unit number 4 is actually fine. The explosion from unit number 4 seems to have occurred from the hydrogen migration from unit 3 over to unit 4 because they shared some common HVAC equipment, some common fans and ducting. So the hydrogen from unit 3 seems to have caused the explosion in unit 4, and the fuel in unit 4 is actually in good shape, and it doesn't seem to have been damaged at all. But there was 3 or 4 days worth of press that said unit 4's got a lot of problems, and we're really worried about unit 4 because it's got plutonium and mixed oxide fuels. So point there is a lot of speculation still going on. There's a lot still to be learned. The one thing that the nuclear industry, not the one thing that the nuclear industry is very good at is we like to pride ourselves in being a learning organization. You know, Fukushima is a very, very significant event. There is going to be a lot that we're going to learn from it here in the future, and I'll get to that. There's probably going to be a lot of changes that we'll make here to help preclude this type of thing from actually happening. What am I doing? Okay, we're moving. Real quickly, let's talk about Pilgrim Station. Operation 72, you can read this in the handout. Pilgrim Station does have one of the highest rating in the nuclear industry. It's an INPO rated plant at excellent. Entergy's invested about $300 million into the plant in capital improvements since we've owned the plant for about 10 years now, a little over 10 years. We're not going to get into plate tectonics, but Pilgrim is not in a seismically active area. In fact, the last significant earthquake in this area was in the 1700s. Anybody live in Middleborough? It was in the Middleborough area, and it was about a 6.0 earthquake. That's a very ancient fault right now. You've seen the plates. Everybody knows that the Pacific plate jumped up underneath the Japanese plate, caused the tsunami. We just don't have that here. And if you look at the satellite imagery, you can actually see the 3 plates there as they converge. And you can see the Pacific plate jumping underneath the plate in Japan. Very few earthquakes on the East Coast as compared to Japan or even the West Coast of the United States right now. Another thing Pilgrim has that we put in about 10 years ago, most of the industries put them in, is a station blackout diesel. The NRC started to ask us, you have all these backup systems, but what if your backups to the backups fail? What if your batteries run out? Fukushima. So we actually have now a station blackout diesel generator that can be the only piece of equipment left, and that's enough power to power up our emergency pumps. So we actually have a 3rd and a 4th level of backup systems. Our diesel fuel oil tanks are underground, but they're above the expected flood, the highest flood. They never had a problem with them in hurricanes, and they have about, I think the plant engineers told me, about 10-foot design, 10 foot of additional margin in the design based on the worst flood we could expect. And we already have portable diesel-driven pumps. One of the interesting things in Japan is they were talking about, well, the plant manager needed permission from the president of the company to order helicopters to get pumps. We practice our emergency drills, and if our plant manager needs something, he's determined he's in an emergency situation, he calls up the phone and he has it. He has that type of authority. We rehearse that and we go through those things as part of our emergency plan. Okay, our operators are licensed. They train on these types of events. We have something called severe accident guidelines where we plan on the regular accidents, and then what if it's a severe accident? What if it's a fire in a part of a plant and you can't get there? What if an earthquake took out this particular section? So our folks actually do train. We don't, if we were to ever see something like this, we have procedures and guidelines in place on how to do it. And that, by the way, includes hostile events after 9/11. We practice on those as well. Industry initiatives, just quickly. Right after Fukushima happened, INPO and the NRC asked the industry, and we were already doing it, to start looking beyond your design basis. We understand what you were designed for, but what if that design fell short? What additional safety margins are there? And we started talking about design basis, station blackout, internal and external flooding. So we looked at all these, and we had to certify to the NRC that we could do these and we could deal with them. The NRC actually came around. They're doing a series of inspections right now. They just released, actually 2 weeks ago, they released their first report, and they determined that the 104 reactors in the United States would be able to cope with this type of event. It didn't say they were perfect. There were issues that needed to be addressed. There were administrative things, lessons learned, and we've currently worked through that. However, the NRC is continuing to conduct inspections. The NRC will issue a full-term report probably about a year from now, and we expect a lot of additional regulatory things that we will need to address that's going to cost the nuclear industry money, just like 3 Mile Island did, just like Chernobyl did. And depending on where those plants operate, whether those costs go on to ratepayers or not, we'll have to see. The merchant plants, the plants that are up here, are merchant. Most probably the utilities are going to have, not the utilities, the companies that own those plants will not be able to recover those, and we'll just have to eat those costs because they're not in a rate base. Spent fuel storage. I'm not sure how many people know this, but in 1983, the operators of nuclear power plants and the federal government, by mandate of the federal government actually, got into a contract where the federal government said, we want to take all the spent nuclear fuel. We want to be in possession of it. We want to make sure there's no nuclear proliferation, and it makes sense to put it all in one place. And the utilities actually contracted with the Department of Energy to accept all this fuel. And the contract said that the DOE would be ready to accept the fuel in 1998. This was the premise of Yucca Mountain and some geological site to store all the spent fuel. It's now 2011. We've all heard where Yucca Mountain, I guess, is not. Massachusetts, last time I checked, Massachusetts ratepayers have paid about $200 million into that fund to the DOE. Don't have much to show for it right now. Entergy and Enstar and the people who used to own these the plants have actually sued the federal government, breach of contract, and have actually gotten some of these monies back and have put them into a fund waiting for somebody to take the fuel. Last year, President Obama commissioned a blue ribbon committee of industry, policymakers, senators, and basically asked them, what do we need to do with the spent fuel? How can we promote nuclear power, looking at the back end of the design? That committee actually issued draft recommendations about 2 weeks ago. And in those draft recommendations, they affirmed that the United States needs to come up with a geological site where we can ultimately store this high-level radioactive fuel. They do it in other countries. I've been to some of those other countries. There is not a technological challenge in doing this. It's a political challenge to getting it done. That's going to take many, many, many years to do. So this committee also recommended that in the interim, we have centralized location. The fuel that goes into the fuel pool is very thermally hot, and after about 5 years, it's not so thermally hot anymore, and you can take it out, and you can put it in a cask or a storage device, and you can put those storage devices on a pad next to the plant. A lot of plants have done that. Vermont has done that. Fitzpatrick has done that, and that's called interim spent fuel storage. But the commission said, you have 104 nuclear plants. Why should each of these nuclear plants have their own individualized spent storage facility? We ought to have centralized spent storage facilities, work through the issues of transporting the nuclear fuel, but it makes much more sense to have 2 or 3 of these centralized locations available, until the geologic final resting place is developed. They also talked about changing the fuel cycle a little bit. In France, the fuel that we store, we could actually reuse portions of that fuel. And so they talked about doing that, which would actually cut down the amount of nuclear fuel that's in the environment. So they recommended that we're doing that. Final recommendations won't be out till probably later this year. Kind of working through that right now. But between, just in summary, 3 points. Nuclear power plants today, at least in the United States, I believe are safe. I've been in the industry for 36 years. NRC affirms that they're safe. We definitely have lessons to learn from Fukushima. We're not at all turning our back on Fukushima. There's a lot of things we can learn and we'll implement there. And if we solve the spent fuel storage, nuclear, at least today, is the only technology we have on a wide-scale basis that we can deploy to significantly make a cut in emissions. Isn't that it? Turn it back to you.